Hi, can you hear me?
Yes.
Okay. Okay, so we were doing a chapter. Let's start. Okay, so we were doing, can you see the lecture?
Yeah, we can see it.
Okay, so we were doing this example in which we were saying that if the frequency is 60 hertz, then in overall impedance, we were seeing the capacitive effect. Okay, so they want us to change the frequency now. So let's change it to if F is 400 hertz, what will happen? So if F is 400 hertz, what things will change? I think resistance will remain the same, but inductance and capacitance will change because they are dependent on the reactance of inductor and capacitance is dependent on omega. So let's see that. So our ZR will be 25 ohms. Our ZL will be J omega L, and our ZC will be minus J over omega C. So J omega L will make it J into 2 pi into 400 into L, which was 20 millihenry. And similarly, it will become minus J over 2 pi into 400 into 50 microfarad. So the answer here will be minus J 7.96, and the answer here will be J 50.27. So you can see that increasing the frequency increases your reactance due to inductor or inductive reactance. But when you were having a lower frequency, you can see that the case was opposite because your inductive reactance is proportional to the frequency. So it means that frequencies change the effect of um, reactance. Like if you increase the frequency, it's going towards the inductor. So the total impedance will be 25 plus J 50.27 minus J 7.96. That will become 25 plus J 42.31. So when you find the magnitude, it will be 49.41 and angle Can you hear me?
Yeah.
Okay, sorry. I don't know why it's stopped. Okay. Okay. Yeah. So what I was saying is that angle, so magnitude will become 49.41 and angle, how we will determine the angle in the Z? What do you think? What will be the angle in this quantity? Can you hear me?
Yeah,
Yeah, we can hear you. I'm just not sure about the answer.
Okay. So what do you think? How did I determine the magnitude here? So as you know, this is A plus JB form. So the magnitude in this case is 25 square plus 42.31 square. And angle theta is 42.31 by 25 tan inverse. So it depends. If you are finding it in degrees, then it will give you in degrees. And if you want to find it in radians, it will give you in radian. So this should be 49.41 and this should be 59.42. Okay? Sounds good?
Yeah, that makes sense.
So at frequency, F is equals to 60 hertz, reactance was capacitive, or X was less than 0. If you see here, it was in terms of negative, which means that it was less than 0. But for F is equals to 400 hertz, X was greater than 0, making it inductive. Sounds good? We are good about this?
Yeah.
Okay. So now I will try to find the like the impedance, like equivalent impedance. If we are given a circuit, how we will determine an equivalent impedance or admittance from that. The point is that if you want to measure the equivalent impedance or admittance, you can you should remember that you can all the time change it. You can all the time change it to the admittance and impedance. Okay. Okay, so this is ENG 212. I will start from here and let me draw a circuit. Can you see the screen? Why this? Can you see the black screen too? No. Okay. Okay. Let me draw a circuit. So if we have this circuit here, which has many storage components like the capacitors and inductor. So how we will find the equivalent impedance? Minus J2 ohms, minus J2 ohms, J6 ohms. Okay, one thing you should remember that if it is given in ohms, then it is in the form of reactance or resistance. But if it is given in Henry and like this, what you should say in the farad, it's in the form of capacitance and inductance. So if it is in the form of capacitance and inductance like the C and H, you have to convert it into the impedance and reactance. But if it is already in the form of impedance and reactance, then you don't have to convert it. Okay?
Okay.
Okay, so now if you see the circuit, when we try to find the equivalent impedance, we just don't want to start from the middle. We start either from here or here. So in this case, I want to start from here and trying to simplify it. But if you see that in this form, this is like the components are in parallel. So I will convert it into the admittance form. Wherever the components are in the series, I will deal with in the impedance form. Okay, so let's try that. Okay, so when I will convert them in the admittance, so first I'll just, for the simplification, I will say that this is my Z1, this is my Z2, this is my Z3, and this is my Z4, which means that the symbolic representation of this is Z4. Okay, so I will convert it in the admittance. I will try to solve it in the admittance because they are in the parallel. And if we try to find the admittance, then they will be just the simply the addition number. So let's try that. So it will be Y4, because Y4 is equals to 1 by Z4 is equal to YL plus YC. So YL plus YC is the admittance of this inductor and this capacitor. So we know that YL will be 1 over J4 and YC will be 1 over minus J2. So I told you that if they are in the ohms form, they are in impedance form. So when they are in impedance form, to find the admittance, we need to find the reciprocal of that. if you are seeing the S, that is like the susceptance or conductance, so then you will say that, oh, they are not in impedance form, they are in admittance form. Okay, so let's try to find that. So if I try to find the LCM, it will be taking minus here. Okay. Okay, sorry. Taking minus 1 over j common and finding the LCM, it will be minus 1 by 2, 1 minus 2. No, should do it like that. 1 over j 4 1 minus 2, right? Is it good?
Yeah.
Okay, and this would become minus 1 by 4j, which will become j by 4s. So it means that if this is in the S form, it means that this is admittance. So this admittance can be expressed as impedance. So to express this admittance in impedance, we will write this as minus j 4 ohms. Why? Because this will be Z4 will be 1 by Y4, and this will become 1 by J by 4, and this will become 1 by J4. So this will become, when J will go up, it will become minus J4. So that's how you will find Z4. Okay, why we are finding Z4? Because we want to add it with Z3, and which is in the series. So we are converting it into Z4. Now, whenever you are seeing a parallel component, you will convert it into the admittance, and whenever you are seeing the series component, you will try to solve it in impedance. So let's try now Z3, 4, because we are adding them up. So Z3 plus Z4. So here Z3 is what? Can you tell me what is Z3? So this is our Z3. Yes?
Yes.
So what is this value?
ZR plus ZL.
Yes. So what it should be?
4 plus J2.
4 plus J2, right? So Z3 is 4 plus J2, and Z4 is minus J4. So it will become this Z34 ohms. Okay, so we are good here. So we have Z34. Now we can see that this total thing is Z34, which is in parallel with this Z2. So we will convert them in the admittance form. So first we will convert it Y34, which will be 1 over 4 minus J2. And whenever we have this thing, we multiply it with the conjugate, and that will give us what you should say. 0.2 plus j 0.1s. Okay, so this is y34. Okay, which means that we can simplify this as first we have done this. This was Z34, Z2, and then now we have combined them and Y234, sorry. No, so this is Y34 yet, and now we will find Y2, sorry. So this is Y34. Now I have to find Y2, where Y2 is. So what is my Y2 here? First, I need to write Z2 here. So what is Z2?
2 plus 6j minus 2j.
Yes, so it will be 2 plus J4. So Z2 is 2 plus J4 and Y2 is 1 over 2 plus J4, which will be equal to, by the same effort that we have done before, it should be equal to or I should do it maybe. So it should be equal to 2 minus J4, 4 plus 16, 22 minus J4 by 20, which will make it 0.1 minus J 0.2s. So this is our Y2. Okay, so now we will add both of them. Y234 will be Y2 plus Y34, and then it will be become 0.1 G 0.2 0.2 plus Y34, which is 0.2 plus J 0.1. Okay, you can see here that when you are seeing this Y2, you don't know that whether this will come as this answer or not. So all the time you need to convert it in the simpler form to find out the simplified answer. Okay, so now Y234. So which will be equal to 0.3 minus J 0.1 S. Okay. Let me confirm. Okay, now, so I have Y234, but what should I do? I combine this. These two, but the next Z1 is in series. So that's why I will convert it back to impedance. That will be equal to, and multiplying it will give me 0.09, I think, and that should be 0.01. So it will become 3 plus J 1 ohms. Sounds good? Are we clear about that?
Yes.
Okay. So Z234 we have, okay. Okay, now the point comes that if you see this, how should I deal this?
Convert them to admittance separately, and then
Yeah.
back to impedance, and then add them to Z234.
Yes. So what we will do it, convert them first in admittance. Yes. So like this would be Y1 YL plus YC. So let's see. Y1 is equals to YL plus YC. YL is no YL plus no YC plus YR. Sorry, this is resistance. So YR is 1, but YC is 1 over minus J2. So what I'm saying is this is R. So YR is 1 plus 1 over minus J2, which will become 2 and or just a minute. We can also write it like this. Okay. So let's go from there, or it could be 1 plus J 0.5 as well. Okay. Now we will find Z1, which will be equal to, why we have to find Z1? Because we are in series with Z234. So which will be equal to 1 plus J 0.5. And it should give us 0.8 minus J 0.4 ohms, Z1. Okay, so now we are in this form. Okay, so our equivalent impedance will be plus 3 plus J1. So it should be 3.8 plus J 0.6 ohms. So that's our equivalent impedance for the circuit. Okay, sounds good?
I'm following you.
Okay. Catherine, do you think it's fine?
Yeah, I think it's fine.
Okay. Okay, so we are good about this. And we just need to take care of few things. One is that when they are parallel, we are dealing with them in admittance. When they are in series, we are dealing with impedance. Other than that, if you have a single number in which you have to do the reciprocal, like if you have this like this J2, and you will just do 1 over J2, it's easy. But if you have something like this, you need to convert it in terms of what you should say, you need to find the reciprocal, so you need to follow proper procedure. So that's what you need to remember when you are trying to simplify the circuit. Other than that, I think it's not difficult to do. Okay, so we are heading towards the end of this chapter, but before that, I want to write a phasor diagram, I think.
Could I ask you a quick question about something before, like in this previous section right here.
Yeah,
You were
go ahead.
doing you were converting like negative j into I think it was I think it was like right there you put 1 over negative j2 and then you made it
Yes.
j over 2. Could you explain how you did that?
Yes.
Is that
So
like a rule, or I think I missed that?
yeah, it's okay. So when we were defining the properties of J, we were saying that it's minus J is 1 over J, right?
Got it. Okay, that completely skipped my mind. Thank you.
It's okay. It's okay. But what like in this case, I can also do like finding the LCM and try to do, but I think it's more easy if I just convert it here because it's not exactly in the reciprocal form. But if there is something like this, like 1 over 2 something, then I have to solve it the other way. So because it's not like that, so it's simpler to do that. Okay?
Okay, sounds good. Thank you.
Mm-hmm. Okay, so I will do a phasor diagram. I think we have done it multiple times, but it's better to do it one more time. So I am solving example number 8.13 to do it the phasor, how we will deal with the phasor. But other than that, if we know angle, magnitudes, and dealing with the complex number, then all the other circuit rules are the same, like nodal analysis and others. So let's try to do the phasor diagram. So this is example 1.8.13. So if we have 3 RLC components in series, like 8.15 figure, so I'll draw this here. This is 1326 microfarad. Okay, so you can see that we have it in terms of inductance and capacitance. So we need to convert them in what you should say impedances. But before that, we are just writing a KVL equation for this circuit. Where we don't know Vs yet. Yes, okay. Okay, so the KVL equation we will write is, if this is Vs, Vs is Vr plus VL plus Vc. Now we know that these are the complex forms, so these are in the bold form because they have in them angle and magnitude both. So this is the bold form. Now I am writing it IR plus omega Li 90 plus I over omega C minus 90. In other words, this is IR plus J omega Li plus minus J over omega C I. I just need to confirm it one more time. Okay. Why I'm writing I in the bold? Because I am thinking that this magnitude and phasor is in this quantity. Let me just confirm it from the previous table that when we are writing, yes, Z in capacitance, it should be minus J over omega C. In other words, what I have done here is, what I was trying to tally it, if you see here in this, not here, in the previous lecture, where is that? What? Yes. So if you see here, this capacitance, like the table, you can see that this is minus J over omega C, ZC. So that's what we have done here. We have said that this is minus J over omega C. And other than that, this is IR plus, or you can also write it like this. So these are all same thing, I'm just saying. ZRI plus ZLI plus ZCI. Sounds good?
Yes.
Okay. So because we have to write the phasor diagram, so we are more concerned with this form, okay? Because in the phasor diagram, you know that we are dealing with the angle or phase. So these two forms, we will not use these two forms, but we will use the form which has the angle. So it means that these two forms are same as this form, but we will be using this form, okay? So that's what is the case here. And now, as we don't know the angle of the current, so we are saying that, let's say our I bold is IM with 0 degrees, okay? Then we will define all the other things with respect to that. If we consider that I am as 0 degrees, so we will know that omega L IM will be greater than I over omega C, IM over omega C, because of course it's directly proportional. Okay, sounds good. So let's define our what they are saying, the phasors first. Okay, so one more thing they have done is they have converted the inductance and capacitances in the impedance forms. So let's see. So we have 15.92 millihenry and 1326 microfarad. So for converting it into the phasor form, we need to have a frequency. So the frequency is 377 radian per second, okay? Which makes it, so radian per second means it is 2 pi f, right? So 377 by 2 pi will give you f, which is 60 hertz. So you can convert, you can find omega L, which is 6, and 1 over omega C is 2. Okay. So now they said that, so we are good with omega L and omega C. We have found that too. And Vs over of t is your 12 square root of 2 cos 377t plus 90 degrees. So we have our Vs as well. That what is the value of Vs? Okay. first I want to, okay, so you can see that our I has the 0 angle, but we have an angle with the VS. But before going into VS, I want to actually draw, before doing this, I want to actually draw a reference, what you should say, phasor, just to make sure that we understand what phasor is here. So let's see. We know that, okay. So if our I is 0 degrees, that we are saying is that our I is 0 degrees, I am. So this would be I here. And another thing you know that VR is IR, which doesn't have any angle in it. So this should also be a 0 degree VR. So VR is also here. And as it is 4, so this will be 4, I am 0 degrees VR, right? I is also I am 0 degrees. Sounds good? We are good about this? VR and I.
Wait, can you explain how you got 0 degrees again?
Yes, so we are given that our current is at 0 degrees. We are assuming, okay, that our current is at 0 degrees, okay?
Okay, why would you assume that?
So what we are trying to do is, if we assume that our current is at 0 degrees, we are setting a reference phasor and we will try to build all the angle around it, okay?
Okay, thank you.
Yes, so it not necessarily be at 0 degrees, but we are just trying to find a basic phasor and then we can convert our, angles. Sounds good?
Yep, thank you.
Okay, now our VL, we need to find our VL. So VL is ZLI, okay, and it was omega LI 90 degrees, but as we know that this is I am 0 degrees, so 90 degrees, so overall angle will be 90 degrees. So this is our VL because it's at 90 degrees. Okay, now we need to see one more thing, which is VC. VC is ZCI, which is minus J over omega C, I, which is 1 over omega C, or I over omega C minus 90 degrees. So this would be our VC. Now we were saying that if what you should say, our VL is greater, if VL is greater than VC, then overall angle becomes inductive. Similarly, if VC is greater than VL, then overall angle will become capacitive. So that's the basic diagram. Like that's the basic diagram of VL and VC we have here. But now we will try to put our, what you should say, original angles to see how this will play out, okay? So another thing in this here is that you can see that your VR, I, and VC is this, okay? And the total angle is VS, which will be the hypotenuse here, because it's the sum of all the angles here. So let's try to put the values in and try to find what is now the value is. Okay, so now we don't know that what are the original values. What we have done, we assumed that, let's say our I is at 0 degrees, then how we will play out with the angles. Okay, so now we are given that our VS is,
Is there any way you can scroll up just a little bit? I missed that. Thank you. Just the VC part, I missed that.
yes, okay. And one more thing is here, one more thing I want to talk about. So let's say if your VL is equal to VC, right? It can be possible that VL and VC magnitudes are equal, which means VL will be equal to minus VC. So they will cancel out each other, right? What I'm saying is that if you have this thing here, and they both are canceling out, then your V is equals to VR. VS is equals to VR. And the phasor will be VR and VS will be in the same direction. But if your VL is not equals to minus VC, right? They will not cancel each other. Then you need to find out which one is greater. Let's say VL is greater, right? Then you will be having a inductive effect that is having that you have VL plus VC in this direction, VR is in this direction, or VS will be in the middle of or acting as an hypotenuse because it will be as A plus JB form. Sounds good? Am I clear about that? Or you want me to explain it again?
I think it makes sense.
Okay. What about who is this? Just a minute. Let me. Doria, do you think it makes sense?
Yeah, I think so.
Okay. So what I'm saying is that if these two have the same quantity, right, then your VS will be in the direction of VR. But if the two are not equal, one of them is greater and one of them is less, then the greater one has its own dominating effect and your VS will be pointing in that direction. Okay. So if your VC is greater than VL, then your dominating effect will be here and your VS will be here. So it depends upon the quantity. So in this case, when they have found that your omega is 377 or your F is 60 hertz, then they said that omega L is 6 and 1 over omega C is 2. So which means that 6 is greater than 2. So it will have the inductive effect. Now, we know that our Vs over of t is 12 square root of 2, 377t plus 90 degrees. Okay. Now we are given Vs of t and we can find I because we don't know I yet. We just assume that I is at 0 degrees and we draw all the phasors around it. But how can we find I? Because we know that our Vs was this. Okay, and this will make it as our ZC is minus j over omega c, which will make it minus j2 ohms, and ZL is j omega L, which will make it j6 ohms. So I am replacing this here, j6 ohms plus no minus J2 ohms plus J6 ohms. Okay. So this will become 4 plus J4 and I. Yes. Okay. So what should I write here in the place of Vs? What do you think? I don't know its rectangular form, like this form. I don't know yet. But I know what is the phasor form of Vs.
(12√2) times 377t plus 90.
Yes, that is the time domain form. This is called a time domain or sinusoidal form. But what is the phasor form? I think we talked about this in the last lecture. Let me see. That how can we write the phasor form of the thing? Okay. Here. Yes, here. So you can see here that this was your V of t, right? Sounds good? Can you hear me?
Yeah,
Yeah,
it sounds good.
sounds good.
So what's its phasor form? Its phasor form was, right, which I have replaced it here, right?
Gotcha.
So in this case, what's the phasor form I should write here?
12√2 less than 90 degrees.
Yes, so the phasor form is I'm doing under root 2 as this. Yes, this is the phasor form. And once I have written the phasor form, I can also write the rectangular form and so on. So let me replace it here. As we have known before, and I think we have done that, we can do multiplication and division by converting it in the polar form or phasor form, whatever you call it. So when we convert this into polar form, this would become, the magnitude will be, and angle will be tan inverse 4 by 4, which will be 45 degrees, and magnitude will be 4 square root of 2. So your I will become 345 degrees. So it sounds that your I, it is not at 0 degrees, but it has some angle. So we will convert all of our phasor or shift all of our phasor according to that. But first you do that, you should remember two things. What we have done here, this is not impedance until we add J's in it, okay, like we have done here. So it's omega L and 1 over omega C, but we know the impedance formula is minus J over omega C and J omega L, which we have converted here. And then we try to solve the question, okay? So now we know that our current is at 345 degrees, which will shift our phasor like this. So previously, let me do it. Previously, So this was when your IM was 0. So you have done this. VR, I, VS, VL, and VC, right? But you were saying that that may be possible that VL plus VC will be in this direction. So now you know that this is not the case. Your IM is at 45 degrees. So which will shift your everything in 45 degrees, which makes your IM VR at 45 degrees and your VS at 90 degrees, that you can confirm here that this VS is at 90 degrees. So your VS is at 90 degree, then your, what you should say, VL will be what? 90 plus 45 degrees, because you have shifted or rotated everything by 45 degrees. So this would be 135 degrees. Sounds good? Or your VC should be at minus 45 degrees. So how will you determine that these angles are correct? You know your VC is minus J over omega C I, right? Sounds good? Where is VC? Yes, this is your VC. So let's check the angle. Okay, so minus J over omega C is becoming minus J2, I think. Minus J2 into I is 345 degrees. So you can write this as 2 minus 90 into 345 degrees, which will become 6 minus 45 degrees. Sounds good?
Yep.
So that's how you know individual phasors, right? Similarly, for VL, you can see that J omega Li, which was 6J, I think, into 345 degree, 6 into 3, 45 degree, and 90 degree, which will make it 18 into 135 degrees. So that will be your VL. So that's how you can, even if you don't understand the rotation, you can individually find the angles. Sounds good? Do we understand this?
Yeah, I think I
Sounds good.
understand. I just have one question. Was was the 12 root 2 given in the problem, or did we calculate that somehow for VS?
No. So what we have done, I'll go through from the start. What we have done here is that we said that we don't know VS yet in the start, okay? So we said we don't know VS. What will be the phasor diagram if we assume that IM is at 0 degrees? So this phasor diagram we have plotted by not knowing VS yet, okay? Then we are given VS here. Okay?
Okay, so it's once it's given once we make that.
Yes. So what we have done here, if you see, that we said that, okay, we don't know VS yet, but we don't know VS yet, but we know VR, VL, and VC without knowing I. So we are just saying that we actually know the impedances, but we don't know I, we don't know VS. So we draw a reference diagram, reference phasor diagram. But once we know Vs, we found a way to find out original current and voltages. So then we plug these values in and we try to find the original phasor diagram. Okay?
Okay, thank you.
Okay, so we are good about phasors. Or no? Are we good about phasors?
I think so, yeah.
Aiden, what do you think about that? Thomas?
Yeah, I get it.
Okay. Sounds good. So this chapter will be ending here and I will post its homework problem. And you know that I was saying, I'm emphasizing this chapter a lot because this is the basis of your AC circuit analysis. So you need to, be very, very sure what you are doing in the problems. I think these problems will help you to solve this. So that is very important that you learn this chapter. And if you don't understand, you can ask, okay? But the thing is that this chapter is very, very important for your AC circuit analysis. Okay. So now I am going back to chapter number 6. Why? This is not a very big chapter, but this will tell us that from where the current and voltages across inductors and capacitors come. So I will just doing this chapter number 6. So let's see, we have a little bit time there. So what is capacitor? First, we will do capacitor. So a capacitor, I think we learned it in the lab too, but is a circuit element that consists of two conducting surfaces or plates separated by non-conducting material. Okay, so if we draw a capacitor, it will be a metal plate, dielectric, metal plate, and this dielectric can be anything, oil, wax, all types of dielectrics we have, glass or ceramic, and allows an electric field to build up. Okay, so we also know that DC current does not flow through capacitor in steady state. Means that once the voltages is built up across it, it will not allow DC current to pass through that. Other than that, we know that Barium, I think there is a material, barium titanate, I think. Let me just quickly confirm it. So there are certain, what you should say, materials, dielectric materials that can hold a large capacitance, that can store a charge, among which this this barium titanate, I think, ensures a large capacitance. So it's the ability to store the charge in the dielectric material that defines the properties of capacitors. So glass or ceramic dielectric material are not suitable for higher frequencies. And there are multiple types of other equipments that defines the quality of the capacitor. Other than that, there is another thing that is called stray capacitance, which you will hear a lot in your circuits. In future, if you have two components very near to each other, what this says that what is stray capacitance? It is unwanted capacitance due to parallel inductors, which are near to each other. So if there are two inductors very near to each other, they can build capacitance among them because air can also act as a dielectric material. So that is an unwanted capacitance that we don't want. Okay, so the capacitance unit, capacitor unit, capacitance we know is measured in farads. Okay, and if you have this Q is equals to CV, where this is your capacitance, and this shows that your C is equal to Q by V, which is Coulomb by volts is equal to 1 farad. Okay. Okay, so, and other than that, we know that capacitors store electric charge, and inductors are the opposite of them, and they store magnetic field. Okay, and they both are energy storage devices. Okay. Another thing is that so in terms of physical outlook of capacitor, how we can define the capacitance, okay? So if you have a capacitor like this, this is your, let's say, capacitor. You have something like this. This is your dielectric. This is your plates. These are your plates. So this will be distance between the plates. This will be area of plates, and dielectric has some permittivity. That is called epsilon. So then if we know all these things, then your capacitance is equals to this, where A is area, epsilon is dielectric permittivity, and D is the distance between the plates. Sounds good? Can you hear me?
Yeah,
Yeah.
sounds good.
Okay, okay. Okay, so we said that charge Q is equal to Q by A of t is equal to CV of t if they are dependent on t. And we also know that we define current as I of t is equals to dq by dt, where current is rate of change of charge. Okay, so now if we replace our relationship of capacitor here, that will make it and that will make it where this is constant value. So that's how we got this current and capacitor relationship, which we were using before. So this is the important relationship to understand. Then if we want to find voltage, that will become V of t is equals to 1 by C. Which this would be the initial condition in the equation. Or you can also write this as and when you will segregate this, it will become 0 and this represents the initial condition before 0 time. Okay, so that's the important relationship which we need to understand with the voltage and capacitors. Another thing we want to define it is power. We know that power is V of t, I of t, which in this case will become this. And energy or work via integration will be so I am just replacing what you should say, trying to integrate the power to find the energy storage in it. And that will be becoming Okay. So this would be 1/2 CV squared T joule. So this expression is basically important for us because this tells us the energy stored in the capacitor. Okay, so the thing is that one more thing I think is important here. That behavior of capacitor you have seen is different in case of DC current and in case of AC current. You have seen that we were all the time talking about capacitor is charged, there is no current flow, but we did not talk about that in case of AC current. So why is that? Let's see. So we said I of t is equal to C dV over dt. But once your voltage is constant, which is in the steady state, when your capacitor has a built-in voltage, has built up voltage due to the voltage source, then this I of t will become 0, because when this will be constant, your derivative will be 0 and your I of t will be 0 and your capacitor will act as an open circuit, which is not in the case of AC current. Why? Because if you plug this here in, where in your AC current, V of t is V sine omega t, then you can see that this will become cos omega t, which is pretty much a quantity that is dependent on time and that will not goes to 0. That's why you are not seeing capacitor passing the 0 current in the AC state, but it's passing, it's not, or it's blocking a DC current in the DC state. Sounds good?
Yes.
Okay. Callis, what do you think?
That's fine.
Okay. So that's very important to realize that that's why we were seeing all the time that, oh, the capacitor is not passing current in DC state. Okay, so now I want to do an example, but I think we will do it next time. So this 6th chapter we will be doing next time. And so pretty much we will be doing the last chapter, that is the 7th chapter, in the last lectures, and we are heading towards the end of this course. And so there will be, I think, 3 more homeworks left for this course. So what I will try to do in the thanks, like this holidays in November, I will try to come up with your grades except your finals, right? So that you can see, or you can have the idea where you are going. Sounds good?
Yeah, that sounds good.
Yep. Thank you very much for today's lecture. Have a good day.
Bye. Have a nice day. Thank you.
Mm-hmm.
Have a good one.